Hello, my name is Bob Devaney. I'd like to talk to you today about some of the incredible things that are occurring in the field of dynamical systems. We all know that the computer has had a tremendous impact in all areas of science and mathematics. It's allowed us to make extensive computations that we never dreamed possible a few years ago. But the computer's had another effect as well. It's allowed us to see images graphically or geometrically that we'd never seen before. This is the point I'd like to stress today. I'd like to show you some of the computer-generated images that come out of the field of dynamical systems. These are images that were seen first by mathematicians barely 10 or a dozen years ago. I'd like to explain what these images mean mathematically, and then go on and tell you how to generate these images. These images come about from trying to understand how systems evolve from simple to complicated behavior, from steady states to turbulent or chaotic states. We want to understand how systems make the transition to chaos. The two images I'd like to talk about are the orbit diagram and the Mandelbrot set. In order to explain them, I have to introduce some ideas from mathematics, namely the notion of iteration, graphical analysis, and then finally some computer experiments that illustrate these images. But before turning to the mathematics, let's look at what these two images look like. What you're looking at here is the orbit diagram. We'll spend the first part of this lecture trying to understand what this image means, but for now, let's just look at it a bit. What you basically see in the orbit diagram is a single curve coming in from the right-hand side, which eventually splits into two curves, or period doubles, and then in turn each of these two curves period doubles again. Beyond that, all you see is a blur on the screen. This is what we know as the chaotic regime. But in between the chaotic regime, we see several small white windows. Now what I'd like to do is magnify this region down here of the orbit diagram. What you'll see first is a single curve coming in, which in turn will period double. So here's the magnification. Look at what you see. This image looks almost identical to the original orbit diagram. We see a single curve coming in from the right, which period doubles, and then period doubles again, followed by the chaotic regime with the white windows interspersed. Now here's the Mandelbrot set. We'll spend the last part of the lecture trying to explain what this image means, but let's explore it a bit. What you basically see in the Mandelbrot set is a large black cardioid-shaped region with little decorations attached. Look here on the left at the little round black decoration that's attached to it, and then a second, smaller little round black decoration attached to it. This actually corresponds to the period doubling regime in the orbit diagram that we saw a moment earlier. Let's magnify that region a bit. Here we're looking at a magnification of that little round black ball, and now you see another smaller decoration attached to it. Let's magnify that decoration. As we continue to magnify, we see smaller and smaller black decorations, and look finally what we see right at the end of these decorations. Look at the small region right here. Let's magnify this region. What we see is another copy of the Mandelbrot set, but look how much different this looks from the original Mandelbrot set. Look at all of the antennas attached to this region. Now let's explore another region in the Mandelbrot set. Let's look at the region that corresponds to the neck between the big black cardioid and the little black ball. Let's magnify that region there. What we see is a whole collection of different looking decorations. Let's zoom in on one of them. This magnification almost looks like a small monster. Let's zoom in on the head of the monster. And now let's zoom in on the eye of the monster. If you look closely at this image, it appears that the eye of the monster is made up of a whole collection of small spiders. Let's zoom in on one of those spiders. When we do, sitting right in the middle of one of the spiders is again another copy of the Mandelbrot set. From these images, you can see that the Mandelbrot set possesses a wealth of intricate geometric detail. It's amazing that in the past 10 years, mathematicians have come to understand this set almost completely. Thanks to the work of Duodie and Hubbard in the early 80s, mathematicians can now look at any small portion of the Mandelbrot set and tell exactly where they are. The geometry of this set is incredible. Both of these images are generated by the simple mathematical function or expression x squared plus a constant. The basic problem is this: given this function, what happens when we iterate this function? To iterate means to repeat a process over and over again. The process repeated, in this case, is iteration of this quadratic function. Basically, what we do is start with a number x and compute its image. That is the number x squared plus a constant. Once we have that number, we do it again. We apply the same function to x squared plus a constant, getting its second image, namely x squared plus a constant, quantity squared, plus the same constant. And then we repeat that over and over again. The third application of the function yields the third point on the orbit of x, and we continue on, iterating to get the fourth point on the orbit, the fifth point, etc. Now, a natural question is, why would anyone iterate a function like x squared plus a constant? Actually, iteration arises in all branches of science and mathematics. Here are some simple examples. For example, just simple mortgage or interest rate or annuity calculations lead to iteration. For example, think of a savings account. If you start with a certain amount of money in a bank and gain interest at each succeeding year, then you calculate the amount of money you have in the bank via a simple iteration. For example, if you start with $100 in the bank at 10% interest, after 1 year, you'll have $100 plus 10% of your original amount, or $110. After the second year, you repeat that calculation. You multiply the amount in the bank by 10% and add it to the original amount. After the third year, you do the same process over. So simple interest problems result in iteration. There are many other examples, though. For example, if you know calculus, one of the major ways of finding roots of functions is Newton's method. Newton's method takes a certain function, the so-called Newton iteration function, and iterates it in order to zero in on, hopefully, the roots of the original function. Other examples of iteration arise in the study of difference equations. We won't get into that very much in this lecture, but here's one example of a difference equation coming from mathematical ecology, from mathematical biology. It's called the logistic equation. Ecologists use it to predict the behavior of populations of certain species. The equation reads quite simply: the population at generation n plus 1 is determined by a knowledge of the population in the preceding generation, in generation n. In fact, the population at generation n plus 1 is given simply as a constant times the previous generation's population times 1 minus the previous generation's population. That is to say, we can determine the population in succeeding generations just by iterating the simple mathematical expression on the right. Finally, there are other areas in which iteration arises. One example is differential equations. If you've studied calculus, you know that most differential equations that arise in science do not have exact solutions. It's impossible to find the solutions of most differential equations. What you do is turn to the computer, which invokes a numerical procedure to solve the differential equation. Most often, that numerical procedure is simply an iterative process. So now let's go back to iteration of the function x squared plus a constant. Let's use the computer to compute various orbits for various c values for this function. This program here allows me to list the orbits of a variety of initial conditions for various values of C. What I'll do is choose 4 random initial conditions, say 0.123, 0.234, 0.345, and 0.456, and then input a particular value of the constant and compute the orbits of these points. So let's begin with C equals 0.5, and now the computer will evaluate the orbits of each of these 4 points under x squared plus 0.5. Here we've listed the orbits of each of those points. Vertically, we see the orbit of 0.123, 0.234, 0.345, and 0.456. And notice what's happened. While the individual numbers here aren't very important, notice that no matter which initial condition we start with, the numbers begin to grow. The 6th point on the orbit of 0.123 is approximately 3, then 11, then 133, and then overflow. That means that the orbit has gotten very large and therefore goes off to infinity. That happens for all 4 of these initial points. A typical initial point will yield overflow, will tend to infinity under iteration of x squared plus 0.5. So let me choose another parameter value. Let's instead look at x squared plus c, where c is minus 0.2. Let's lower the parameter value now. If we start the iteration and compute the orbits of each of those points, you see something completely different. Notice that the orbit of 0.123 eventually gets very close to minus 0.17. Similarly, the orbit of 0.234 gets close to minus 0.17, as does 0.345 and 0.456. Typical orbits near 0 for this function don't go off to infinity. Rather, they seem to converge to one fixed point. Let's do another experiment. Now let's lower the parameter a little further. Let's look at x squared plus minus 0.9. Let's compute the orbits of those same 4 points under iteration of this function. When we do that, we see that the orbits no longer tend to one fixed point. Rather, they tend to oscillate back and forth between 2 points. Let's observe that by looking not at the first few points at the orbits, but rather points near the 50th iteration. You see that by iteration number 49, the orbit of 0.123 is near minus 0.11. Then it hops to minus 0.88. Similarly, the same thing happens for 0.234, 345, and 456. Each of these orbits eventually cycles back and forth between minus 0.1 and minus 0.8, minus 0.1 and minus 0.8. So we see very different behavior as we begin to lower the value of the constant. Let's do one more experiment. Let's compute not the value of c minus 0.9, but rather say minus 1.31. Again, the same orbits for x squared minus 1.31. When we compute those orbits, you see something completely different. Let me again look down at iterations near 49 and 50. And what you see is, instead of cycling back and forth between 2 points, these orbits all tend to cycle back and forth between 4 points. At iteration 45, we're at 0.0012. At iteration 49, we're back at the same point. So we see that instead of cycling between 2 points, orbits of x squared minus 1.31 tend to cycle back and forth between 4 points. What we're observing is the beginning of the period doubling route to chaos. One more example. Let's lower the parameter even further. Let's choose x squared minus 2, and again compute those same orbits. And what we see here is something quite a bit different. If we look down near the 50th iteration, you see that no longer are these orbits tending to cycle around. No longer is there regular behavior. Rather, all 4 of these orbits are behaving quite differently. This is the beginning of the notion of chaotic behavior. So let's try to summarize what we've just seen. We've seen that for iteration of x squared plus 0.5, typical initial conditions have orbits that tend off to infinity. On the other hand, when we lower the value of c down to minus 0.2, this behavior changes. We saw that typical orbits for x squared minus 0.2 tend to one fixed point. They tend to be attracted to a fixed point. Now, as we continue to lower the value of the parameter down to minus 0.9, we again see a change. Instead of being attracted to one fixed point, orbits are now attracted to a cycle of period 2. They tend to bounce back and forth between two different numbers. As we continue to lower the parameter, we again see a change. When c is minus 1.31, we saw that typical orbits were attracted to a 4 cycle. They tended to bounce back and forth between 4 different numbers. As we continue on and lower the parameter down to c equals minus 2, however, this pattern is broken, and we see behavior that's quite a bit different. Instead of behaving in a regular fashion, orbits tend to essentially run randomly through different numbers. This is, I said, the beginning of the notion of chaotic behavior. Now, it may appear that the program that I was using to generate orbits was quite sophisticated. In fact, the programs to generate orbits are quite simple. Here's a basic program to generate the first 50 points on the orbit of x squared minus 2. It's very simple. We simply input the initial value x, whose orbit we're going to compute, and then in 50 steps successively compute x squared minus 2, and then replace that value as the new x value, and repeat. So this program, the program to list orbits, is really quite simple. I should remark that the programs to generate the Mandelbrot set and the orbit diagram are not really that much more complicated. The programs involved in dynamics are fairly simple to write, fairly short. So let's try to explain all of this. I use a process called graphical analysis to geometrically realize the orbits of a function x squared plus c. What I have here is the graph of x squared plus c. Here I've chosen a c value relatively large, about 1/2. In fact, any c value larger than 1/4 will work. I've superimposed on this graph the diagonal line, the 45-degree line, the line y equals x. Now, how do I use this picture to see geometrically the orbits of x squared plus c? Here's the way. Let's start with a typical point, say x naught, and try to see geometrically what the orbit of x naught looks like. How do I do that? Well, I've first got to compute the image of x naught under the function. To do that, I look vertically up to the graph of the function. The y-coordinate of the point on the graph of the function is the image of x naught, is x naught squared plus c. So if I now draw a horizontal line back to the diagonal, I reach the point whose y-coordinate is x naught squared plus c, but whose x-coordinate is exactly the same. That is, I reach the point directly over the number x1, the second point on the orbit of x naught. Now, how do I get the next point on the orbit of x naught? Well, I repeat that process. I compute x1 squared plus c by going vertically to the graph, and then I project horizontally to the diagonal, reaching the point directly over x1 squared plus c, which is nothing but the next point on the orbit. And then I continue. To get the next point on the orbit, I go vertically to the graph and horizontally to the diagonal, and then again, go vertically to the graph and horizontally to the diagonal. What you see quite clearly is that for c values that are larger than 1/4, the orbit of any x naught goes off to infinity. That's something we saw quite clearly in the computer experiments a moment ago. Now let's go back to the computer to speed up this process of graphical analysis. Let's begin by applying graphical analysis to x squared minus 0.2. Remember, that was the parameter value for which we saw typical orbits converging to one fixed point. Let's see that happening via graphical analysis. I've drawn here the graph of x squared minus 0.2. I've eliminated both the x and y axes. You recall from the previous picture, though, that the y-axis ran vertically right through the minimum of this function. The horizontal axis is more or less right about here. So let's apply graphical analysis by choosing a typical x value, say the x value right here, and then computing its orbit by going to the graph and then over repeatedly. There we see the graph of x. You go vertically to the graph, horizontally to the diagonal, to the graph and over, to the graph and over, to the graph and over. What you see is a typical orbit is attracted down to this point, the point of intersection of the graph with the diagonal. That's an attracting fixed point for this function. Notice that if I start with an x somewhat to the left, the orbit of that x also tends in to the attracting fixed point. Now let's change the parameter a bit. Let's go down to c is minus 0.9. Recall that for that parameter value, typical orbits converge to a cycle of period 2. Let's see that graphically. There's the graph of x squared minus 0.9. Let's now choose an x value very close to this fixed point and do graphical analysis. You see that the orbit cycles around for a while and then seems to settle down. Let me remove the first few points on this orbit. Let me remove the tangents. And what you see left is a box. That's a cycle of period 2 because if I start with this x value and go vertically to the graph and over, there's one iteration, then do it again, I end up exactly where I started. That's a cycle of period 2, and we see that typical x values are attracted to that cycle of period 2 under iteration. Now let's lower c again. Let's lower c down to minus 1.31 and compute the orbit of a typical x value here, say x here. When I compute the orbit of that x, again, you see some transient behavior, but eventually the orbits settle down on, if I remove those transients, a cycle of period 4. You see that because if I start with this point, go vertically to the graph and over, then again to the graph and over, to the graph and over, I end up after 4 iterations at where I started. So a typical orbit has been attracted to a cycle of now period 4. Finally, let's iterate x squared minus 2. Let me compute 234 points on the orbit of a typical point under x squared minus 2 and see what happens. There's the orbit of that x value, and notice that it never settles down. Rather, it tends to run almost randomly around the interval without ever closing up. This is, again, the beginning of the notion of chaos. Now let's try to put all of this information together. What I'll do is use the computer to paint the picture of the orbit diagram for x squared plus a constant. What the orbit diagram is basically the asymptotic orbit of 0 for a variety of different c values. I'll plot these c values on the horizontal axis between minus 2 and 0.25, and I'll plot the orbit of 0 on the vertical axis between minus 2 and 2. What the asymptotic orbit means is I'll essentially throw away the first few iterations of the orbit of 0. I'll remove the tangents, much as we did with graphical analysis. Why I choose the orbit of 0 I'll explain in a bit. So, what will the orbit diagram look like? Recall from our previous computer experiment that when c is minus 0.2, typical orbits were attracted to one fixed point. So in the orbit diagram, on the vertical line directly over minus 0.2, we'd expect to see just 1 point. In fact, if we look at any c value between 0.25 on the right and minus 3/4 on the left, you'll see that the orbit of 0 is attracted to one attracting fixed point. That's why we see a single curve in the orbit diagram over those c values. On the other hand, as c decreases, we then see that the orbit of 0 will be attracted to a cycle of period 2, thereby giving 2 points over each such c value in the orbit diagram. As c decreases further, we expect to see that the orbit of 0 is attracted to a cycle of period 4. So our orbit diagram should look much as we've drawn in this picture here. So now let's turn to the computer to see the computer draw the orbit diagram. What this program does is compute the orbit diagram for x squared plus c for c values starting at 0.25 and decreasing down to minus 2. For a variety of different c values equally spaced between these two limits, we'll compute 125 iterations on the orbit of 0. However, we'll not display the first 35 iterations. We'll throw away those transients. So let me now draw the diagram. What you see here printing to the right near c equals 0.25 and below is one single line. Remember, on each vertical axis we're plotting the asymptotic orbit of 0, so that corresponds to what we know to be an attracting fixed point. As we continue to plot, we see that all of a sudden the orbit of 0 stops being attracted to a fixed point and is now attracted to a cycle of period 2. Continuing to let c decrease, we see that this orbit period doubles again, and then doubles again, and then goes into the chaotic regime. Let me simply note that there's a window here to the left that appears to consist of an orbit that has 1, 2, and 3 points on it. That is a cycle of period 3. I'll come back to that in a minute, but before that, let me enlarge a portion of this orbit diagram. Let me magnify the region that I've enclosed in a box here. So let me compute the orbit diagram, but restricted to this small box. When I magnify it, we again see 1 point coming in. But since this is the picture in the small, we know that that's a cycle of period 2, which then bifurcates to a cycle of period 4, and then to period 8, and into the chaotic regime. And even though this is a small portion of the orbit diagram, notice again that we have this window that seems to consist of 3 distinct orbits. Let's do one more magnification. Let me magnify this portion of the orbit diagram. When I do, we see essentially the same image again. In comes a cycle of now period 4, which changes to a cycle of period 8, then to 16, then to the chaotic regime. Up pops a window of period 3, and we're done. Now let me go back to the original diagram. I'll change the number of iterations back to 125, and the original window from minus 2 to 0.25, and draw the diagram again. As before, we see the attracting fixed point, followed by the cycle of period 2, period double to 4, and then, as we know, on and beyond 8, 16, the chaotic regime, and finally the window of period 3. Let's try to magnify that window of period 3. let me draw a small rectangle around the window that appears to be period 3. It's hard to see that rectangle, but let's magnify it. When we stretch those C values out, we first see a chaotic regime, but then all of a sudden, emerging from the chaotic regime, we see just 3 points over any C value. And then look what happens. That period 3 orbit splits into a period 6 orbit, and then appears to period double again, and then boom, back into the chaotic regime. What do you think will happen if we magnify one of these period 3 regimes? Well, as you can see, when we magnify that small portion of the orbit diagram, we're going to see essentially the original picture again. This now is a period 3 orbit, which splits into a period 6, then doubles again to period 12, then into the chaotic regime. Up pops a little window that looks like period 3, and we're done. Let's turn now to 3 very interesting facts concerning the orbit diagram. First fact concerns why we use the orbit of 0 to plot the orbit diagram. Well, 0 is the critical point for x squared plus c. That means 0 is the minimum for the parabola x squared plus c. It's the place where the derivative of x squared plus c is 0. And the fact is that if a function like x squared plus c has an attracting cycle, then a critical point must be attracted to it. So if x squared plus c has an attracting cycle, then 0 must tend to it. So the orbit of 0 always finds the attracting cycles. In particular, this also implies that x squared plus c can have at most one attracting cycle. This function can't have an attracting cycle of period 5 and another attracting cycle of period 35. Now, that might not impress you right now, but let me turn to the second fact concerning x squared plus c, and indeed any continuous function of the real line. This is Sharkovsky's theorem. This is an incredible theorem that was proved in 1964 by the Soviet mathematician A.N. Sharkovsky, and what it says is this. Let's list all of the natural numbers in the following rather bizarre way. Let's start by listing all of the odd numbers except 1. So we list 3, and then 5, 7, 9, etc. When we're done doing that, let's list 2 times all of the odds. So 2 times 3, 2 times 5, 2 times 7, etc. And then list 4 times all the odds, followed by 8 times all the odds, and in general 2 to the nth times all the odds. When we're done listing all of those numbers, we've listed all of the natural numbers with the exception of 2 to the n times 1. So let's finally list them in reverse order. So we list 2 to the n, followed by all the way down to 2 cubed, 2 squared, to the first, and at the end of the list, 2 to the 0, or 1. Now, what's Sharkovsky's theorem? Sharkovsky's theorem says this. If a continuous function has an n cycle for any number n, and n happens to precede some number k in this list, in the Sharkovsky ordering, then that function must also have a k cycle. Now think of what that means. It says that if your function has a cycle of period 20, that's 4 times 5, then that function must also have cycles of all other periods. 4 times 7, 4 times 9, 8 times 3, 8 times 5, etc., all the way down to all the periods a power of 2. Moreover, this theorem is amazing because it's valid for not just x squared plus a constant, but in fact for any continuous function of a real line. Any continuous function of a real line must satisfy the Sharkovsky ordering. Notice also what it says. Period 3 is at the head of the list, whereas periods a power of 2 are at the end of the list. So Sharkovsky's theorem says that if your function happens to have a cycle of period 3, then it must have cycles of all other periods. Cycles of period 5, 7, 9, all the way down through the Sharkovsky ordering. That's incredibly powerful. Think of what it says for our orbit diagram. For our orbit diagram for x squared plus c, for certain c values, we saw an attracting 3 cycle. We saw no other cycles whatsoever. Yet Sharkovsky's theorem says they must be there. They must be there lurking somewhere, cycles of all periods for all n. Another consequence of Sharkovsky's theorem is the fact that the periods a power of 2 head the list. That means if we have a function with very few cycles, then those cycles must all be powers of 2. That is to say, simple functions, functions that are dynamically simple, must make the transition to chaos by going through, at first, a sequence of period doublings. Period doublings is the way functions increase in their complexity in terms of the dynamics. Now, it may seem that this period doubling is a strictly mathematical phenomenon. The fact is that period doubling has been seen in a large number of physical systems that make the transition from simple to chaotic behavior. One such experiment was done by the physicist Harry Swinney and his group at the University of Texas. It involved the measurement of the electrical charge fluctuations in a chemical reaction known as the Belousov-Zhabotinsky reaction. This film shows the apparatus used in the experiment as well as the plotting of the data. Here are 3 excerpts from this graph. Notice at one time the period or number of oscillations needed to return to the maximum voltage was 1. Later the period doubled to 2, and then still later the period doubled to 4. Continuing in this manner, the fluctuations eventually became chaotic. A final observation is one that was made by the physicist Feigenbaum in the late 70s. Let's go back to the orbit diagram and look again at the period 2 and period 4 windows. Let's compare the widths of these 2 windows. Notice that the period 2 window seems to be, roughly speaking, about 4 or 5 times as wide as the following period 4 window. Now let's zoom in on the period 4 window and observe the same situation. So here's the magnification. Here's the period 4 window, followed by the period 8 window. And again, we observe that the period 4 window seems to be about 4 or 5 times as wide as the corresponding period 8 window. So we see that these successive magnifications not only have a topological or qualitative self-similarity, but there also seems to be a geometric rigidity involved. That's the result of Feigenbaum. Let's try to make all of this precise. Let me let A1 denote the length of the C interval where x squared plus c has an attracting fixed point. Recall that from the orbit diagram that extended from c equals 0.25 down to c equals minus 0.75. Let's let A2 denote the length of the C interval for which x squared plus c has a 2 cycle, A3 the length of the C interval for which it has a 4 cycle, etc. Feigenbaum's observation was that the ratios ak divided by ak plus 1 tended to a limit, 4.669, and that limit was independent of the family of functions. If you take any function that period doubles its way to chaos, then the lengths of the respective windows in which period doublings occur have ratios which tend to exactly that same number, 4.669. This was eventually proved by Collet, Ekman, and Lanford only a few years ago. Now let's turn to the Mandelbrot set. As with the orbit diagram, the Mandelbrot set involves iteration of a quadratic function. This time, however, the quadratic function is no longer real, but rather complex. We'll iterate the function z squared plus c, where both z and c are complex numbers. We'll write z as the complex number x plus iy, and c as the complex number c1 plus I c2. That is, c1 is the real part of c, and c2 is the imaginary part of c. So computing the orbits of z squared plus c basically means squaring the complex number x plus iy, then adding the complex number c1 plus I c2 to it, as I've done here. Now there's one major difference between orbits in the complex plane and orbits on the real line. We can no longer use graphical analysis to describe the orbits of a complex function. For example, let's look at the orbit of 0 under iteration of z squared plus c. Okay, if we take 0 and square it and add c, we reach the complex number c, wherever that happens to be. If we now take that complex number and square it and add c, we reach a new complex number. That is, orbits of points under complex iteration are simply sequences of points in the plane. If we now take c squared plus c and apply the function over and over again, we continue with a sequence of points in the plane. Now, for a typical c value, there are only two possibilities for the behavior of the orbit of 0. Either the orbit of 0 can escape to infinity under iteration of z squared plus c, or it does not. So either we have the orbit of 0 being an escape orbit or a non-escape orbit. The Mandelbrot set turns out to be the set of all c values for which the orbit of 0 does not escape to infinity. The set of all c values for which the orbit of 0 remains in a bounded piece of the plane. So that then gives us the algorithm for computing the Mandelbrot set. What we basically do is search for those c values for which the corresponding orbit of 0 does not escape to infinity. Those c values are then in the Mandelbrot set. So we'll select a grid in the complex c plane. Each point in this grid will represent a complex number c. For each such grid point, we'll select c and compute the corresponding orbit of 0. If that orbit of 0 escapes, the corresponding c value is not in the Mandelbrot set, and we'll color c. So colored c values correspond to points that are not in the Mandelbrot set. On the other hand, if the orbit of 0 never escapes, then we'll leave the corresponding c value black. We won't light the pixel corresponding to c. That means that c is in the Mandelbrot set. Now the only question that's left is, what do the colors mean? The colors simply mean this. If I shade a point red or orange, that means that the corresponding orbit of 0 has escaped to infinity very quickly, after only a few iterations. On the other hand, if the corresponding point is shaded blue or violet, that means it's taken the corresponding orbit of 0 a long time to escape to infinity, but it has escaped to infinity, so the corresponding c value does not lie in the Mandelbrot set. One final word, what does it mean to escape to infinity? It turns out it's a mathematical fact that if an orbit of 0 escapes beyond the circle of radius 2 for a c value inside the circle of radius 2, then we know that that orbit must tend to infinity. So all we have to do is check whether the corresponding orbit of 0 ever escapes from the circle of radius 2, and we're guaranteed that the corresponding c value is not in the Mandelbrot set. So now let's turn to the computer experiments and see how the Mandelbrot set unfolds. So here we see a computer-generated image of the Mandelbrot set. Remember, the black points correspond to points in the Mandelbrot set. The colored points are points outside the Mandelbrot set. For the record, this image extends from -2 to +2 in both the x and y direction in the plane. Let's take another tour of the Mandelbrot set by zooming in on various portions of this picture. For example, we might zoom in on the topmost piece that I've highlighted here. When we zoom in on that region, we see a little black decoration with an antenna attached to it. We'll later call this decoration the period 3 bulb. Note for the record that the antenna splits into 2 pieces. If we zoom in on this little black blotch on the antenna, we see another copy of the Mandelbrot set, this one with antennas attached to it. Now let's zoom in on another area of the Mandelbrot set. If we zoom in on this piece on the right, on this decoration on the right, we again see a black decoration with an antenna attached. We'll later call this the period 4 bulb. Notice that its antenna splits into now 3 pieces. Again, if we zoom in on the little black blotch on the antenna, we find another copy of the Mandelbrot set. One more zoom. If we zoom in on the decoration on the left-hand side of the Mandelbrot set, this is what we'll call the period 5 bulb. Notice that its antenna splits into 4 different pieces. Finally, if we look at the tail of the Mandelbrot set, we look at that small region way out on the left tail of the Mandelbrot set and expand it, we see another copy of the Mandelbrot set. We'll see later that the c values that lie in this small Mandelbrot set actually correspond to the period 3 window in the orbit diagram that we saw before. The obvious question is, why do we use the orbit of 0 to plot the Mandelbrot set? There are actually 2 reasons for that. The first we've seen before, that is, if the quadratic function z squared plus c has an attracting cycle, then the orbit of 0 must be attracted to it. In particular, it can't go to infinity, so this c value is in the Mandelbrot set. We'll see in a moment that that explains the terminology, the period 3 and period 4 decorations on the Mandelbrot set. The second reason is more important. In fact, the orbit of 0 determines the shape of the set of all other orbits which do not go to infinity. What happens to the orbit of 0 determines the structure of this set, which we'll later call the filled-in Julia set. But first, let's return to the first reason and see what attracting cycles say about the Mandelbrot set. Here's an outline of the Mandelbrot set. Let me orient you a bit in the plane. The real line, a set of c values that are real, runs right down through the spine of the Mandelbrot set. Also, the imaginary axis runs vertically more or less right about through here. The entire picture is contained within the circle of radius 2 in the plane. Now, as we know, any c value that has an attracting cycle must be in the Mandelbrot set because the corresponding orbit of 0 is attracted to that cycle. So it turns out that that's the meaning of the little bulbs or decorations that hang off the Mandelbrot set. Each c value in a given bulb has essentially the same dynamics. In particular, all of the c values in one of those decorations are attracted to a cycle of some given period. In particular, if we take any C value inside the main cardioid, the main body of the Mandelbrot set, then the corresponding orbits of 0 must be attracted to an attracting fixed point, or a cycle of period 1. If we take any C value in this secondary circular region, then the corresponding orbits of 0 must be attracted to cycles of period 2. If we look at any C value in the upper or lower decorations, then the corresponding orbits of 0 are always attracted to cycles of period 3. If we look inside regions that sit approximately here, then for those C values, the orbit of 0 tends to cycles of period 4. Same thing over here. C values in this smaller circular region always tend to cycles of period 4. Now look at this little blip right here. We saw in the computer experiments earlier that this little blip actually corresponded to a Mandelbrot set. In fact, the main cardioid of that smaller Mandelbrot set features C values that have cycles of period 3. So we see that all of these decorations have a very definite dynamical meaning. They correspond to the behavior of the orbit of 0 in terms of which cycle it's attracted to. So this idea finally allows us to explain the intimate relationship between the orbit diagram and the Mandelbrot set. What I've done here is superimpose those two images, but remember the real line, the real C values for the Mandelbrot set run right along the spine of the Mandelbrot set. What I've done is align those C values, those real C values, with the corresponding values for the orbit diagram. In particular, the value C equals 1/4 is right here at the cusp of the cardioid, whereas C equals -2 is right here at the tip of the tail of the Mandelbrot set. Now look what we see. For the corresponding C values for which the function z squared plus c had an attracting fixed point, they sit directly above the corresponding C values for the orbit diagram. Similarly, what we call the period 2 bulb correspond exactly to the C values for which x squared plus c has an attracting 2 cycle, and so forth. The period 4 bulb corresponds to the period 4 window, and so on. Way down here, we noted the baby Mandelbrot set, whose cardioid had period 3. Notice that that sits directly above the period 3 window in the orbit diagram. Attached to the cardioid in the period 3 Mandelbrot set were all the secondary period doubling bifurcations, which we also viewed in the period 3 window. Finally, let me explain the remark that the orbit of 0 determines the shape of the set of all orbits which don't escape under z squared plus c. This is the notion of the filled Julia set. What we'll do is fix a complex C value and then iterate z squared plus c on a variety of starting z values. So we're fixing C and computing the orbits of different z values. Now when we do that, one of two things can happen. Either the orbit of z will escape, or the orbit of z will not escape. The filled Julia set consists of those z values whose orbits do not escape to infinity under iteration of z squared plus c. So it's important to remember that for different c values, we get very different filled Julia sets. There's an absolutely amazing fact that occurs. For the filled Julia sets of z squared plus c, there's really only two possibilities for what they look like. Either the filled Julia set is a connected set, consists of just one piece. The only other possibility is the filled Julia set consists of infinitely many pieces. The filled Julia sets cannot, for example, consist of 2 pieces, or 5 pieces, or 30 pieces. One piece or infinitely many pieces. Now, it's the orbit of 0 that determines which case we're in. For if the orbit of 0 fails to escape to infinity, for example, is attracted to an attracting cycle, then the fact is that the filled Julia set, the set of orbits that don't escape, must be connected, consist of just one piece. On the other hand, if the orbit of 0 does escape to infinity, then the filled Julia set must consist of infinitely many pieces. In this latter case, we'll see that the infinitely many pieces are actually infinitely many scattered points, what we call a Cantor set, sort of a dust of points in the plane. So this gives us a completely different interpretation of the Mandelbrot set. The Mandelbrot set is also the set of C values in the complex plane for which the corresponding filled Julia set is connected, is just one piece. If a C value is not in the Mandelbrot set, then the corresponding filled Julia set has infinitely many pieces. So now let's finally turn back to the computer and look at a few of these filled Julia sets. What we'll do is select a C value from the Mandelbrot set and then compute a number of orbits of Z for this C value. The algorithm we'll use is exactly the same as before. If the orbit of Z escapes to infinity, we'll color that point. On the other hand, if the orbit of Z fails to escape to infinity, that is, Z is in the filled Julia set, we'll leave that point black. So black points correspond to the filled Julia set, colored points correspond to the complement of the filled Julia set, and the coloring gives us the rate of escape of that point to infinity. So let's choose a C value from the Mandelbrot set. Suppose we choose a C value just about here. The C value I've selected is given in these windows in exponential notations. It's approximately the C value 0.15 plus 0.22i. So let's compute the filled Julia set for that C value. I'll use a maximum of 25 iterations to decide whether the corresponding orbit escapes to infinity or does not. So here we're computing the filled Julia set for Z squared plus C. Remind you that black points correspond to points whose orbits do not escape, or in the filled Julia set. Colored points correspond to points whose orbits do escape, and the colors give us the rate of escape to infinity. You'll notice that this filled-in Julia set consists of just one big black blob. That's because we chose C from the interior of the cardioid of the Mandelbrot set. Let's instead choose a C value just outside the Mandelbrot set. For example, here I've chosen the C value 0.4 plus 0i. So a C value on the real axis for which the orbit of 0 escapes, and as we've said, the corresponding filled Julia set shatters to infinitely many pieces. Let's draw this Julia set. Notice that we see very little black whatsoever. The black regions are hidden among the blue and violet regions. They're very sparse. They do consist of infinitely many points, however. Here's another example. Let's choose a C value within the period 2 bulb of the Mandelbrot set. I've chosen approximately the value -1 plus or minus 0.01i, so close to -1. Let's draw its Julia set. Again, you see that the filled Julia set is a large black region that's connected. Quite a bit different in shape, however, from the previous filled Julia set. Sort of looks like an infinite snowman lying down. On the other hand, if we choose a C value outside of the Mandelbrot set, in the neck of the region between the main cardioid and the period 2 bulb, and draw its Julia set, again, the Julia set shatters into infinitely many pieces. Finally, let's select a C value within the period 3 bulb. When I compute its filled Julia set, we again see one big connected blob. Again, the configuration is quite a bit different from the previous filled Julia set. Sort of looks like an infinite rabbit. Main body in the rabbit with 2 ears sticking up and down. Then there are ears attached to to those ears, and so forth. So we see that in each different bulb on the Mandelbrot set, the filled Julia set assumes a very different shape. Let's now animate all of this. What I'd like to do is show you a film of how the filled Julia sets change as we follow a continuous path which wends its way through the Mandelbrot set and outside of it. Here is the path that we'll take in the Mandelbrot set. We'll go right down the spine of the Mandelbrot set through the main cardioid into the period doubling regime and beyond, and then exit, returning near the period 3 bulb, exit again, returning near the period 4 bulb, and then return to the Mandelbrot set right through the point c equals 1/4. Then we'll go vertically up through the period 3 bulb, through its period 6 region, and then out. So here are the corresponding filled Julia sets to that motion. Here we're outside the Mandelbrot set, then all of a sudden, boom, at c equals 1/4 we enter the Mandelbrot set. Here's where we experience period doubling, and then we period double again. Now let's come back to the period 2 region, and now we'll exit the Mandelbrot set. Watch how the Julia set shatters, changes shape very quickly, and becomes a scatter of points, a Cantor set of points. These points move around until we re-enter the Mandelbrot set at the period 3 bulb, in which case a black connected region reforms. Exiting again, we have a Cantor set. Then we touch the period 4 bulb right here, big black region, which again shatters as we leave. Notice that some black regions persist because we used only 35 iterations to check whether a point escaped to infinity. Some points take longer than 35 iterations to escape and are therefore not in the filled Julia set. Here we return through the point c equals 1/4. All of a sudden the filled Julia set becomes large and connected. Julia set changes shape as we go into the period 3 bulb, and then into the period doubling region beyond it, and then out of the Mandelbrot set.